And Jay is from Ohio State. Let me just say the one paragraph thing. Ohio State, he is the academic lead for the new Ohio State Global Water Institute, GWI, I guess. And there's an interesting colleague of his that I met and who used to work at Huntsville, Alabama, and you can imagine what he did there. And his name is, it went right on my head, Marty Kress. And he's a very dynamic guy that it's interesting that I think it's very unique that Ohio State took this approach of hiring a guy that was an administrator type to form an organization and get it going and then bringing in the faculty side of it alongside of it. So it was a very unique approach.
Thank you, Stan. Thanks for having me in Gainesville. I am a UF alum, so it's always nice to come back to Gainesville and see some old friends once in a while, and I've been able to do that for breakfast and dinners while I've been down here, so thanks for inviting me, Stan. As Stan said, I am from Ohio State University. I'm a professor in the Department of Food, Agricultural, and Biological Engineering. Been there for 15 years or so. So today what I'd like to do is briefly introduce you to the Global Water Initiative, which Stan mentioned, and then I want to spend the bulk of time talking about data analysis and integration related to water quality and agricultural landscapes. We're doing some work on that in Ohio State, and I think there's some lessons to be learned that are relevant to what we're talking about today. Okay, so I'd like to start out by just defining 3 global water challenges, and a lot of these have been mentioned earlier today. So the first of those is water security. We all know this is a global problem. Quite a few other people have mentioned it today. And when you look at the World Economic Forum, they actually identified water security as being the most important global risk in 2015, so ahead of terrorism and all the other stuff that we worry about. So a very important thing, global scale, obviously. Moving on to another global water challenge is coastal resiliency. This is a photo of Hurricane Katrina in 2005 from New Orleans. My wife is from New Orleans. I spend a good bit of time there myself, so something that hits home for me personally a little bit. And as our coastal populations increase, as the coastal storms become stronger, as sea level rise continues to happen, we'll be even more challenged to design and better adapt coastal cities to these types of threats. And then lastly, this has a little more relevance to Ohio, but also very important across the globe is our harmful algal blooms and coastal eutrophication. Looking across the globe, there's more than 700 coastal areas that suffer from coastal eutrophication, overabundance of nutrients, and harmful algal blooms are very common amongst those 700 sites. So this is something that's very important in Ohio. I'm going to talk about it a bit more later, but also has global ramifications as well. And so, as Ohio State moves to become the land grant of the future, we want to not only look at regional state problems such as the harmful algal blooms, but we want to look at global problems and address those as well. So that's where we get into our water supply crisis. So there we have a program called Wells to Wellness. We have Field to Faucet, which is addressing harmful algal blooms, and lastly, coastal resiliency. So those are the 3 thrusts that we have within the Global Water Initiative at Ohio State. And I'm just briefly going to talk a little bit about those 3. First, starting with Wells to Wellness. So we've initially decided to focus in Tanzania. The agricultural college of which I'm a part of at Ohio State has a pretty long relationship with Tanzania, so it was a logical place for us to start out. And looking just at Tanzania, there's approximately 5,000 non-functional wells. One of the earlier speakers spoke about, is it better to do something than do nothing? But you really need to have a long-term plan. And what a lot of NGOs have done is they've gone in and installed drinking water wells in developing countries. And then after half a year, 2 years, these drinking water wells stop to function. Maybe parts become cannibalized to sell for scrap metal. Maybe a part breaks. For whatever reason, a lot of the drinking water wells stop working within the first couple years, if not sooner. So the thing we want to do is build capacity to restore these drinking water wells. So we want to build the supply network so that they can get the pieces they need. We want to build the expertise starting in the universities so that they have the expertise to repair these systems. Build that network so they can repair these systems. So we've started with 45 wells. You can see those, I hope, on the right-hand side. Those are the 45 wells we're going to initially start with. And then we eventually want to expand the remaining wells. And in the future, we'd like to move on from water to power and economic development, but water is our entry here. So moving on to coastal resiliency. To be honest with you, this is the area where we've done the least amount of work. We have built some key collaborations, mostly thanks to partnerships with Stan. We've been partnering, Stan mentioned, in the Netherlands, so we've worked in the UNESCO Coastal Resiliency Collaborative and also a part of the UN RISE network. So I'm not going to belabor that too much. Moving on to field of faucet, and this is what's nearest to my research, so I'm going to talk a little bit more about this today. So field of faucet, addressing harmful algal blooms within the state of Ohio and then eventually looking globally. So how many of you heard of what happened in Toledo in 2014? Show of hands. I'm always interested to see how many people know about this outside of Ohio. So maybe half of you have heard of this. So we've been having harmful algal blooms on Lake Erie for more than a decade, almost every year, since probably the early 2000s, maybe actually late 1990s, so maybe almost 2 decades. In 2014, we had the record-setting harmful algal bloom. We just had another record-setting harmful algal bloom in 2015, so these are growing in severity. In 2014, the harmful algal bloom, part of it was located over the water intake to the city of Toledo, so they had to shut down their potable water for 4 days. And this cut off drinking water to 400,000 people for 4 days. So very quickly, this went from a problem which affected people that go to the beaches, fishermen, tourism, to something that affected everyone. Couldn't take showers, restaurants couldn't open, businesses were closed, so it had a huge economic impact. As a result of that, there are new state laws in Ohio that govern what farmers can do. There's also new approaches for water treatment to remove some of these microcystins, the toxins that are affiliated with harmful algal blooms. This was a real watershed event, to use a water analogy there, and it really drove a lot of things in the state of Ohio and beyond. And it wasn't just a drinking water ban in Toledo. I'm going to move this wire before I hurt myself here. In Toledo, we had a drinking water ban in 2014. There's also one on Paley Island in the middle of the lake, in Monroe, Michigan in 2014. In 2013, in Carroll Township along the little further southeast in Ohio. So you can see what the extent of the harmful algal bloom looked like that year. You can see what it looks like when somebody holds it up in their hand. That's the water intake for the city of Toledo right behind that. So you could see that there was a heavy concentration of algae that year. So these problems are growing. You see here's 2013, 2014. When we look at what's going to happen with climate change, we should have heavier spring storms in northwest Ohio, which is going to bring more water, more nutrients into Lake Erie. So these harmful algal blooms are going to be with us for a while. So we can either do nothing and have the harmful algal blooms grow bigger, or we can start to do some things in Ohio. And so really quickly, I'd just like to walk you through how we're defining the problem right now, our best understanding of the problem right now, what's guiding some of the things we're doing. So what are we focused on? So we're focused on dissolved phosphorus. And why are we focused on dissolved phosphorus? Well, we've seen some important trends happening. And if you look at the top right here, you'll see that the dissolved phosphorus coming out of the Mommy River is the biggest watershed that feeds into western Lake Erie. You see that prior to 1995, for those 20 years, we see a decrease in dissolved reactive phosphorus from maybe 0.1 milligram per liter down to 0.04. But then beginning in 1995, we see an increase. And in fact, the concentration that we see in that river is almost doubled over that time. And then when we move down to the bottom half of the screen, where we multiply our discharge times our mean concentration, and we actually figure out the load of phosphorus going into the lake, we can see that that's doubled since 1995. So prior to 1995, that load was going down. When we look at it from 1995 to present, we see that it's about doubled from maybe 300 metric tons per year to closer to 600 metric tons per year. So we're seeing a lot more dissolved phosphorus going into Lake Erie than we've seen in the past. And we see really strong trends if we look at the amount of cyanobacteria, or the amount of harmful algal blooms, is on the y-axis here, and the amount of soluble reactive phosphorus is on the bottom axis. We see really strong correlations there. So there's some kind of strong connection between the amount of phosphorus going in and the amount of harmful algae that we see in the lake. So based on these trends, and there's a lot more data behind that, I'm just showing you a couple things there. A couple management agencies, the Lake Erie Phosphorus Task Force here in 2013, more recently, US EPA Annex 4 has, both of these groups have arrived at very similar recommendations, basically recommending a reduction of both total phosphorus and dissolved phosphorus of about 40%. Okay, that's a big change. But that's what they say we need to get these harmful algal blooms at some kind of reasonable level. And so we need to reduce the phosphorus. So how are we going to do that? What's the source of this phosphorus? Where are we going to look to cut back on the phosphorus coming into the lake? And the answer to that is agricultural runoff. And why am I pointing my finger at agriculture? And we try not to do that. I'm in agricultural college at Ohio State, so we try to have good relationships with the agricultural community, just as I'm sure IFAS does, but have to be truthful at times. And the main reason why is because we look at what's happening within the landscape. So if you look at the center here, the tributaries to Lake Erie, Western Basin, 70% of that landscape is covered by row crops. That's corn and soybeans in our neck of the woods. So it's not only the coverage, but it's also, we have data that show where the phosphorus is coming from and things like that. So we're working mostly with the agricultural community and farmers to try to reduce the amount of phosphorus coming into the lake. And a good example, that's the Mommy Watershed, and that's what we see here highlighted in white. In the Mommy, if you look up in the upper right here, it's actually 85% agriculture. And this is the largest watershed in the Great Lakes, about 17,000 kilometers squared. It is the watershed that drives what happens in Lake Erie. All the other watersheds pale in comparison to what's happening here. The amount of phosphorus that comes in from the Mommy Watershed, it is half of the phosphorus that comes into Lake Erie. In contrast, the amount of water that comes down from Detroit, from the northern Great Lakes, brings about 90% of the water into Lake Erie, but only about 30% of the phosphorus. So there's really high concentrations of phosphorus and big loads of phosphorus that come in from the Mommy River. So how are we going about tackling this problem to reduce the amount of phosphorus coming in? And this goes back to something that was mentioned just a couple talks ago, is that we found it's really important to not focus on social systems, not focus on engineering applications, ecological applications, but try to look at these social ecological systems if we want to try to solve this problem. It can't be solved with one disciplinary approach alone. You have to look at interdisciplinary solutions. So with that in mind, a few years ago, I led an effort at Ohio State to get some funding from the National Science Coupled Human and Natural Systems program to look at an interdisciplinary approach, to look at how social systems, physical systems, ecological systems can look at those systems together to try to better understand and make strides to improve water quality in Lake Erie. So if you look at the kind of the upper left-hand side of this image, that's where the social side is. And what I'd like to do is show some data from the social side, show some data and analysis from the bottom of this graph, where we have our watershed analysis, looking at the more physical side, and look at ways that we're coupling those disciplines together. And I'll go ahead and kind of give you the take-home message here. And the take-home message is that we have made pretty good strides in looking at individual problems, or looking within one discipline here. So looking at the social side, looking at the engineering side, the watershed modeling side. we've made good strides there, but the problem is still integration. So how do you merge social data? How do you merge watershed data to try to answer these bigger questions about how do you improve water quality across the basin? And I think that in academic settings, we're still struggling with that. And this isn't just my perception, but I've talked to other people working on similar problems, and they all report that, within the disciplines, they're making great progress, but it's really hard to pull the rabbit out of the hat at the end, or to integrate across these different disciplines. So starting on the social science side, we've done a lot of surveys across the Mommy Basin, and this is just one snapshot here that I'm showing you. And I'll highlight one result here, and just to emphasize the importance of this. So one of the best management practices that we've spent a good bit of time looking at are called drainage management systems, and this is a way for farmers to control how much water comes out of the drainage tiles. Almost all of the Mommy Basin's drained, going back 100, 150 years. It was called the Great Black Swamp. It's not a swamp anymore. It's corn and soybean fields. But the only way you can make an old swamp productive is you have to drain it. So there's drainage throughout. So if you can hold some of that water back in the drains, you can hold back phosphorus. But when we look at the probability of adoption of this practice, we see that 48% of the farmers are unlikely to adopt it, and 10% say they're never going to adopt it. So that's kind of discouraging. This is one of the best practices that we've found. Half the farmers are not going to use it. So then we can go back and talk to the farmers and say, well, what are the constraints? Why are you not interested in using this practice? And we find out, well, first one, everyone can probably guess, is money. It costs money to put in the structures to do this. The second one is time. It takes time to go in and physically raise the weir boards up to hold the water back or let the water out. So then we can start to address those constraints. We can maybe have cost shares to help farmers implement these devices, or maybe we can automate the raising of the weir boards so it takes less time. So we can use that data to help the farmers implement this practice. Taking it a step further, we can actually develop some predictive models here. So we can look at farmer characteristics. So how big is your farm? What's your ideology? How old are you? So we can use those types of things as predictors. We can also look at contextual data. So how far is the farm from Lake Erie? We find that has a significance on how much of an environmental ethic the farmer might have. Are you closer to a large town or not? So using these types of data, we can actually predict the likelihood of a farmer to want to adopt drainage water management, or the likelihood of them to adopt or not adopt different practices. So again, within this discipline, we're making good predictive models and developing some good capacity there. So here's a little quiz for you. Who can tell me what this is a picture of here? It's the Block O, right, from Ohio State. I didn't know Ohio State's not having a good year in football, so I didn't know if anyone would be aware, but this is one of our logos here, so that's our logo. Yeah, Buckeyes are poisonous. Did you know that? Okay. So what's making this Block O? Sugar. we don't have much sugar cane in Ohio. Not fertilizer, nope. Corn. It's two different hybrids of corn, actually. So, and up to the top half of the screen is Interstate 70, so you can see some tractor trailers up there to give you an idea of the scale here. So, basically, this is I guess you would call this an agricultural stunt or something like that, but it demonstrates the capacity, I think, of precision agriculture and data. So right now, with precision agriculture, we can tell a planter exactly where to plant what seed to do crazy things like this that aren't very practical, but we can also do really practical things. So we can tell it what type of hybrid of corn to plant on the outside of rows that's going to capture the side light, what type of corn to plant in the middle of fields that's going to just capture light from the top, what type of corn or soybeans to plant, different soil, different slopes, all kinds of stuff like that. So there's huge capacity there. what I think there's a lot of capacity, and it's not realized yet, is to have environmental benefits as well. So water quality, environmental improvements. So how can we use this type of capacity to improve water quality? And I think some of the low-hanging fruit is looking at testing the soil. So right now, one of the problems with soil tests is that they're very coarse. Their spatial scale is very coarse. So maybe you have one soil test for every 25 acres. So you know with each 25-acre block what kind of soil you have and how much fertilizer to put on that, what type of corn hybrid to put on that 25 acres. But you have this type of capacity to dictate where you put the fertilizer and where you put the seeds. So how do you merge that? How do you make soil tests more available and cheaper for farmers so that they can know exactly what the soil's like, maybe within each 10-foot block or something, and then plant accordingly, and then and apply fertilizer accordingly. Then you would limit how much phosphorus is going to come off the landscape. So the point is here, there's a huge potential here, not only to have agronomic benefits using precision agriculture, but also environmental benefits as well. And one of the things that we're trying to do to realize some of that is developing some apps that farmers can use. So one of the things is just to allow farmers to record their practices in an easy way. So lots of farmers have handheld devices in the cabs of their tractors now. So how can they record these practices and they go back and look at them year after year? How can they get information about weather, about soil very easily and put it in the cab of their tractor where they can use it? So we're trying to develop some of these applications so that farmers can record this data and benefit from it. The next step is to access this data on a much larger scale, and we're working on that at Ohio State now too, where we're developing what we call a data warehouse that's going to be in the cloud somewhere, wherever that is, where you'll be able to aggregate some of this data, and that could benefit farmers. They can see what's going on within their whole county, and they can see what types of practices are yielding the best results. It can also have really good benefits for watershed modelers such as me, so you can have an idea of what's happening across the landscape at some kind of aggregated level, much better data than we have right now. We can look and we can have satellite data to show, is it corn or soybeans this year? Is it a forest? Is it an agricultural crop? But we don't know the practices. We don't know what type of tillage is being used, what type of fertilizer application rates being used. So that type of information would be really helpful to us as we try to move forward. And if we can encourage farmers to store that information and then find ways that we can protect their anonymity, but we can still benefit from that information at some kind of aggregated scale, it could be really beneficial. And one step to do that is to have these apps that farmers can utilize. And the last area I want to talk about is kind of the physical side, and that's the watershed modeling and data. And I'm going to start by showing you, this is Western Lake Erie Basin. These are all the rivers that flow into that western part of Lake Erie. And here you can see all of the water quality stations and stream gauges within those watersheds. And actually looking across the world, it's probably one of the best, some of the best modeled or monitored watersheds looking across the world, as I mentioned. The pity is that while there's maybe 40 or so triangles here that show different stations, only a handful of these have a long enough record that we can actually use it and get a trend. So due to the recent events in Lake Erie, we have put in more of these, and there's a commitment to keep gathering this data from more of these sites. We should build more capacity over time. But right now we have about 5 sites that have a long enough record that they're actually useful. And one of those sites is the one that pours into Lake Erie, and that's the site that's given us the information I showed you before about the dissolved reactive phosphorus concentration. And that goes all the way back to 1950. So we do have a good record from some of these sites. And important for me and for others, we can use this data to develop and calibrate and validate watershed models. And these watershed models, if we know or can predict what the rainfall is, we know the soil quality, we know the farming practices, we can predict how much water is going to come off that field and go into the streams, how much phosphorus, how much nitrogen, and things like that. So then we can go back and we can test different best management plans to see, okay, if 40% of the farmers adopt drainage water management, it's going to reduce phosphorus by this much coming into Lake Erie. And so that's what we've been doing here. And on the bottom, this is a bit busy graph here, so I'll try to orient you to it here. So on the bottom of this graph is some of the best management plans that we've looked at. So there's fertilizer placement here is one of the most promising things we've looked at. A common practice in Northwest Ohio right now is broadcast fertilizer. So you put phosphorus on, just like you were putting phosphorus fertilizer on your lawn, you spray pellets on the field. And then when it rains, the pellets wash off and go into the river. So placement just means that you're taking that fertilizer and placing it in the soil instead of putting it on the surface, and we found huge benefits for that. And there's other ones, I'm not going to go through them all, but 50% less phosphorus, applying in the spring versus applying in the fall, rye cover crops. So that's what you see on the bottom of this. What we've done is we've used a multi-watershed modeling approach. So a lot of you are familiar with climate change models, so we don't just use one climate change model, we use 20 or 30 of those because we know there's a lot of variability in climate change models. And so we try to use an ensemble approach. Well, and we're actually doing that with these watershed models. There's been so much interest in Western Lake Erie Basin that we've found that there's actually 5 or 6 of us with very similar watershed models. And so we've worked together to develop an ensemble approach for watershed modeling. And by doing this, we can get these error bars, these predictions, so we get more robust predictions than just using one model. So we can make much stronger recommendations to managers about which BMPs will work and which ones won't work. And so this is kind of where we are with the watershed modeling. Now, we are making linkages kind of across disciplines here where we're working with economists. And working with economists, we can start to answer the questions of, is the investment in these BMPs, is it worth it? So using the watershed model, we can find out what coverage of BMPs we would need to get such a reduction in phosphorus. So if we want 40% reduction, we can find out that we need to have 35% of the basin covered with some kind of management practice. And then we can find out, okay, that management practice costs so much. We can find out how much it would cost to implement that level of the BMP. On the economic side, we can estimate what will be the impacts of improving the water quality in Lake Erie with that. So we can relate water quality to housing values and fisheries and things like that. So by merging this watershed modeling approach with economics, we can start to answer the question of, is the investment worth it? And that's a pretty important question. A lot of people want to know the answer to that. So just to reiterate, I think that we've made some good strides here within our disciplines, collecting good data and using that to make some conclusions, but I think there's still a challenge with integrating between the social sciences and the engineering and the ecology to try to answer the bigger questions. And I guess with that, I'll leave it. So thanks a lot. Stan, can I take questions? Yeah. Okay.
I see a lot of parallels between what's happening in Lake Erie and what you're talking about, and exactly what happened before. Very similar. The everybody's agricultural area had phosphorus was thrown up and went down to the lakes, caused sounds, born ponds. Turns out it either reduced phosphorus to 10 micrograms per liter. I think the graph you're showing was like 50 was about the threshold where you start getting blue-green algae, the cyanobacteria in Lake Erie. The different, and I listed a whole bunch of BMPs for the farmers. The difference is that the legislature in Florida says you must implement these BMPs if you're down the EA to protect the everglades, so it's a mandatory thing. And probably, that was that analysis we did about approximately 20, 25 years, there's a 65% load reduction between the pre-BMP years and the post-BMP years, just following, and just like what you're saying, the water management BMP was extremely effective, keeping that water on the property, banning application of fertilizer, make sure it gets to the root zone before. Real similar things. They actually work if the farmers will implement them. Now, they were forced to in Florida. I don't know, do you guys have a Team GL program up there that forces agriculture to adopt BMPs to be the same compliance, or is it a little bit different in Ohio?
That's a great question. So just to summarize, I think your question is, So in Florida, it worked to have regulations which forced the farmers to adopt these BMPs and put them in, and it fixed it. It was very successful. Looking at the Everglades, what's going on in Ohio right now. In Ohio right now, we're having a very similar discussion. Is voluntary adoption, is that going to work? And that's where we're at right now. The agricultural lobby in Ohio is very strong. Politically, it's going to be really hard to get any kind of regulation passed. So right now, more hands go up. So I think that if, this is just me speaking, if we had another event like Toledo, I think, things would start to happen. When Toledo did happen, there were some bills passed in the state legislature banning manure application on frozen ground and some of the real obvious things that most farmers weren't doing. If we could eliminate surface application of phosphorus, that would be huge. If we could just get rid of that. So right now I think a lot of us think that we need regulation, but the political climate just won't support that right now, unfortunately.
You're all going to say that.
Well, it's a comment, it's not so much a question. In South Florida, the legislature mandated that to the farmer because of the litigation, the potential litigation. Just wondering, was there any lawsuit and how this? That's really what's going to make a political machine.
You're right, we're Sue happy in Florida. I guess you guys are Sue.
It hasn't happened yet, but Toledo and especially some of the drinking water plants are considering that, because right now the responsibility falls to the drinking water treatment plants. They have to invest heavily, and it's really expensive to remove these toxins, and so they're considering it. But I think they also are. They're also aware of how things stand politically, and so, I think if it gets bad enough, it'll happen. So if we have another Toledo event, something like that, I think something like that would probably happen.
It's a violation of the Clean Water Act, but it's for a lawsuit.
Mm-hmm.
So it's not a state issue, it's a federal law, not a private.
I think it's just how powerful the ag lobby or the Republicans that have been in control of Ohio for a while, or whatever your political persuasion is there, but there's several groups that want the governor of Ohio to declare Lake Erie a threatened, or put a tag on it. I think it's threatened or something like that, and that would bring in more federal money and things like that. But that hasn't even happened. So.
Let me ask you a question and give you just a brief context for it. Like, a lot of what you just described is exactly what we're dealing with Lake Okeechobee. Right? The twist is that Lake Okeechobee, water flows in from the top, and the water flows out from the bottom. So it's like a double-faceted issue. With you guys, you're just dealing with what's flowing into the lake. So what we're finding is that the term we use is called legacy phosphorus. I don't know if you're familiar with that term.
Yeah.
So all the long-term historical stuff that's been applied in the northern watershed for decades. And then all the dairies that used to be there, was a dairy buyout program, etc. All that stuff is still there, and it's still being imported. So it's like, if you don't control what's getting in on your side, at some point it all runs off in the lake, and then you have to effectively put it downstream. So from a historical perspective, how are you guys dealing with legacy phosphorus? Or just kind of records, are you seeing upcoming trends in your phosphorus or decreasing trends, etc.?
So we also have the issue of legacy phosphorus in two ways, I guess. One is legacy phosphorus on the landscape. So we have there's a lot of dairies and old dairies, and when you do the soil tests, we haven't done nearly enough soil tests, but you'll soil test around and you'll find some real hot spots where that place is going to be leaking phosphorus for a century probably, and there you just have to catch as much as you can with BMPs at the edge. And so one thing is we need to identify where those are in the landscape. And then we also have legacy phosphorus in the lake itself, because a lot of the phosphorus is settled out. It's in the sediment. As long as we keep it aerobic, it won't be released very fast. But we also have a problem of hypoxia in Lake Erie. And so if that grows, then we'll have more phosphorus coming out of those sediments. So we definitely have the problem of legacy phosphorus as well. So.
The whole issue boils down to that we found in South Florida that you are dealing with something that will not go away, and every BMP is designed for containment. Containment is the issue, so just don't let it move.
One final point, you guys, the relationship between global climate change and this is really close, because cyanobacteria are going to outcompete every other algae at 30 degrees C. You're getting a lot more 30 degrees C days up there now that everything's warming up, where diatoms are like 18 degrees that can be common. So the warmer it gets, all those cyanobacteria is going to move up more than we've had in Florida for years. But welcome to the new reality, I guess.
Yeah, and I think that's one of the reasons why we're seeing bigger algal blooms, not just due to changes in rainfall, which is also something that's happening with climate change, but just the warming of the lake. The earlier warming and the longer falls, it just opens up that window when the algae can grow and exist. So, and we're doing some of that work. It was mentioned in that messy diagram up there, but I just didn't have time to talk about it. But we are looking at some of the climate change impacts as well.
One thing I wanted to ask about, given the geography of here in that area, are the Canadians doing anything from the north side? How does it compare with?
You know, the Canadians are interested. I think when you look at the inputs and what's causing the problem, I think it's mostly what's happening within the U.S. and largely Northwest Ohio. So I didn't show you all the relationships, but there's really tight relationships just from what's flowing in from the Mommy River to how big the harmful algal bloom is every year. What happens in Ontario, it's not terribly important. Hopefully, at least not terribly important with regards to the water quality in Lake Erie. There's a lot of neat things happening at a bigger scale. It is, yeah. Yeah, and they're engaged. We have meetings with them and things like that. But when you look at the flow of water and the flow of nutrients, just do a mass balance around Lake Erie, you quickly see where the phosphorus is coming from and where it needs to be reduced.
And is the shallowness of Lake Erie?
Oh, yeah. Yeah, so, I mean, I didn't go through it all, but Lake Erie is the shallowest, most productive, smallest Great Lake, but also has the biggest fishery. It also has the most people that live around it. So it's the shallowness of Lake Erie. It's also the most southern lake, so it's the warmest, with harmful algal blooms. And so it's a perfect environment for harmful algal blooms. It's really shallow. You put in a bunch of nutrients in the summer, it gets warm. Wham, you got harmful algal blooms. Yeah, the shallowness plays a big part. Sherry?
I just wanted to clarify something that Russ said, where it made it sound like BMPs in the state of Florida are mandatory. They're only mandatory for areas where there's lawsuits. It's not mandatory throughout the entire state. That program is a voluntary program, and in order to address that cultural divide or the resistance that you were coming across in Ohio, we just throw money at it. So the water management districts, for instance, have cost-share programs, and they're targeted at agricultural entities and farmers, growers, and we give them 75 to 90% of the cost of projects to do water conservation, to implement any BMP, to do nutrient reductions, those kinds of things. So I don't want you to think that we rely on regulation in the state of Florida to reduce or to increase BMPs or to reduce phosphorus loads. We just really, truly throw money at them. Tell them they have to come up with a little tiny amount of money to pay for a huge project.
And we're doing that in Northwest Ohio. The NRCS is really active in cost share plans for drainage water management and other BMPs, like I mentioned before. The problem is there's just not enough money. So there was a recent grant that came. I think it was $17 million, a partnership between Ohio, Indiana, and Michigan, and there was some kind of yearly awards. And I think that there were going to be 100 awards given to farmers, and they had 700 applications, which is promising. There's more farmers that want to do it, but we just need a bigger pot of money.
Brian just made a good point. We have 3 national parks downstream of the Everglades, so we get a lot of money from that.
Have you, some folks at UF are looking at taking imagery and defining whether submerged aquatic vegetation has a lot of algae on it or not. And I saw in your picture, if a farmer uses a cell phone to take a picture of his field, if there's yellow corn areas and there's green corn areas, you're developing apps. You could develop an app to tell him where he needs to sample for his maximum or minimum soil nutrients based on the cell picture.
Yeah, well, I'm not sure if farmers are using cell pictures, but they're actually using drones now to fly over their fields and identify areas where they need more or less fertilizer and things like that. So that's happening. Yeah, there's targeted soil sampling, but it's just not. It's just time intensive. There's no machine. There's no robot that goes out there and collects soil samples every 10 square feet or 10 square meters or whatever. It's usually a very coarse scale. And so it doesn't match up with the ability of this precision ag to implement the agriculture, implement the fertilizers, or put the fertilizers down. So there's kind of a mix of scales right there. Where we have the ability to put the fertilizer and seeds exactly where we want, but we just don't have the knowledge as to what type of soil is there, what type or what the nutrient concentration is in that soil.
You can use the imagery, and then with sampling just the maximum and minimum, know what the range is, and map the whole field at one time instead of just.
Instead of sampling the soil, you sample the plants every year. And that's a good idea.
Equip your drones with fertilizer missiles and you're done.
Yeah. Kansas State has a drone program that they're working on for that.